In today's lesson, we're going to be talking about derivatives of logarithmic functions. So notice here, the first thing we want to show is the derivative of ln of x is 1 over x. Well, how do we show that? Starting us off here, suppose y equals the ln of x. Well, if y equals the ln of x, then we know that e to the y would be equal to e to the ln of x. But using our logarithmic properties, we know that e to the ln of x is just x. So therefore, we have e to the y equals x. We're going to take the derivative with respect to x. If I take the derivative across this equation with respect to x, we get e to the y times, that was not with respect to x, so using implicit differentiation, this becomes dy dx. And now the derivative with respect to x of x is just 1. Isolating and solving for dy dx, we get 1 over e to the y. But as we just stated here earlier, e to the y equals x, so therefore dy dx is equal to 1 over x. So therefore we have shown the derivative of the ln of x is 1 over x. Let's take a look at some other derivatives. In this next example here, we want to show that the derivative of b to the x, so any base, is going to be b to the x times ln of b. To see this, make the following observation. E to the ln of b is equal to b. Therefore, if I want to take the derivative with respect to x of b to the x, that's equivalent to taking the derivative with respect to x of e ln of b times x. But we know that the derivative of an exponential is itself times the derivative, in this case using the chain rule of the top, will just be the ln of b. Rewriting this, we get e ln of b to the power of x times ln of b. And using our logarithmic properties again, e ln of b is just b to the x times ln of b. So therefore we have shown that the derivative of b to the x is b to the x ln b. Let's try another derivative. For our final derivative here, we want to show log base b of x is equal to 1 over x ln b. To show this, let y equal log base b of x. Therefore, writing this in exponential form, we have b to the y is going to be x. Now, taking the derivative with respect to y here, we have the derivative of b to the y is going to be itself times ln of the base. But now we did not take the derivative with respect to x, we took it with respect to y, so we have to tack on a dy dx using the chain rule. And that technique there is your implicit differentiation. And now the derivative of x with respect to x is just 1. Solving for dy dx here, we get dy dx is equal to 1 over b to the y ln of b. Since y is defined to be log b of x, we have dy dx is going to equal 1 over b log of b to the x times the ln of b, but we know that b to the power of log b of x, using our logarithmic properties, just simplifies to become x, and we end up getting the derivative of log bx is 1 over x ln b. So now that we have our three derivatives, let's take a look at some examples. For the first example here, we want to take the derivative of f at x equaling ln of the cos of x. So if we take our derivative, f prime at x is going to be what? Well, the derivative of ln, if you recall, is 1 over x. So therefore, the derivative of ln of cos of x would be 1 over the cos of x. But now I have to apply the chain rule and take the derivative of the cos of x, in which case that is negative sine of x. So therefore, f prime at x would be negative tan of x. Let's try another. For this question here, we want to take the derivative of ln of x over the square root of x plus 1. You're going to want to apply your logarithmic properties here. Notice we'll have to end up using the quotient rule to take the derivative of this in its current form. So let's go ahead and use our logarithmic properties. So this will be actually equal to the derivative of ln of x minus the ln of the square root of x plus 1, which our derivative properties continue here. This will be ln of x minus the ln of x plus 1, the power of a half. And then I can also rewrite this and drop down that half, and this becomes the ln of x plus 1. Continuing on here, now we can take the derivative. The derivative of ln of x, as we know, is just 1 over x. And the derivative of this expression here, the half will come out. And now the derivative of ln of x plus 1 is 1 over x plus 1. Rewriting this, we have 1 over x minus 1/2 times 1 over x plus 1. Putting this together and getting a common denominator, we get, notice after getting a common denominator, I then distributed the 2 into the binomial. I then just collected like terms, and our simplified derivative is x plus 2 over 2x times x plus 1. So for this question here, recall, for y equals b to the x, the derivative is b to the x times ln of b, so ln of that base. So in this case here, your base is viewed as the 2, and your x value is viewed as the x squared. So if I take my derivative, in this case y prime, it's going to be b to the x, so in this case 2 times x squared. Now again, the chain rule kicks in here. I have to take the derivative of x squared, in which case it's 2, and then you take the ln of 2. So y prime in this case would be 2 ln 2 x times 2 to the x squared. And again, normally you put any constant terms out front. All right, let's try another. So for this question here, again, whenever you're taking the derivative of these lns or logarithms or exponentials, you want to look to see if there's any properties. Well, I know that I can drop down this 4, right? I can drop that down using my logarithmic properties, and this becomes 4 log of base 10 acting on 3x plus 4. It's a lot easier to handle here. We don't have to now use the power rule. So now if I go ahead and take my derivative here, we get y prime equals, and recall here, for y equals log base b of x, y prime is going to be 1 over x ln b. So in this case here, this is exactly what we did. Base was 10 in this case, and my input was 3x plus 4. So we did 1 over 3x plus 4 times a ln of that base. In this case, it was 10. For the next problem here, we want to find the derivative of the following. So for this one here, we have g at x is f at ln of x. So therefore, g prime at x would be f prime at the ln of x times, chain rule kicks in, you have to take the derivative of the inside, in which case the derivative of ln of x is just 1 over x. Likewise, for part b here, g prime at x, well, the derivative of any exponential is itself, so this will be e to the f at x, times the derivative, using the chain rule, of the top would be f prime at x. Let's take a look at another example. So for the following example here, we want to find all points on this curve where the tangent is horizontal. So we go ahead and take our derivative. In this case here, this will be dy dx is going to be 2 ln of x plus 4. Now notice here, this 2 is acting on the entire function, not just on the x plus 4. Had the 2 been applied to just the x plus 4, we could use our logarithmic properties and drop down that 2 and make the derivative easier. This is not the case here. So using the power rule, we have 2 ln of x plus 4 times the derivative of the inside is going to be 1 over x plus 4 times chain rule kicks in again, and the derivative of x plus 4, as we just said, was just 1. So therefore, dy dx, in this case, is going to be 2 ln x plus 4 over x plus 4. We go ahead and set that equal to 0, and now we want to solve. Well, this is equal to 0 at what values? This is equal to 0 where the ln of x plus 4 is equal to 0. Well, when is the ln of x plus 4 equal to 0? Recall your ln is just a logarithm of base e, and solving this logarithmic equation, this would be equivalent to e to the 0 is x plus 4, in which case x is e to the 0 minus 4, so x is equal to negative 3. So now that I have my x value of minus 3, I can go ahead and sub that into my original function to find the corresponding y value. Subbing this in here, we end up taking the ln of 1, which is 0. So the point is negative 3, 0, where the curve, ln of x plus 4, quantity squared, is horizontal. That concludes today's lesson. Thank you.